Listen-only mode.
Hello, everyone. Welcome back to the 10th broadcast in the hands-on workshop series, Programming and Optimization with Intel Architecture. As usual, I will do a quick review of the course material, and also I will show you a few additional new resources. So we are today in day 10, and earlier we discussed parallel architectures and focused on Intel Xeon and Intel Xeon Phi coprocessors. We talked about how to run something on Xeon Phi and how to run something in parallel, both on Xeon and on Xeon Phi. And we, after that, had a very extensive exploration of optimization techniques for applications running both on the Xeon architecture and on the Xeon Phi architecture. Today, I have two software development tools that I was going to present to you. This workshop has a web page, and from this web page, which is this one, you can obtain the slides, the code that we are dealing with, and also you can get recordings of earlier sessions. So this is this page as it is now. Recordings up till yesterday have been posted, and slides are right here. While I have the web browser open, I wanted to show something new. If you have just joined us, or maybe you joined us a couple of sessions ago, you wish you had joined earlier, well, of course, you always have the option of viewing earlier episodes. Also, you can register for one of the upcoming workshops just like this. There's one coming up in October, and one opened just today is coming up in November. So maybe you joined us too late. Maybe you didn't get remote access and you wanted to. These are the other opportunities. And while I have the web browser open still, let me show you one more resource. If you search in any search engine for Intel Modern Code Challenge, this is a contest that Intel has recently opened. This contest is open to students. It comes with really nice prizes, including a trip to CERN and an internship with a scholarship. The nature of the contest is performance optimization. They give you uh, an application from natural sciences, and they ask you to optimize it for performance on the Xeon Phi architecture. Colfax is actually providing computing infrastructure for this contest. And there's, I think, already tens to maybe hundreds of people signed up. So if you're a student, check this out. Back to our course. This course is based on the book Parallel Programming and Optimization with Intel Xeon Phi coprocessors, available here. The book is the source of all the exercises that we are doing. If you would like a really concise written discussion of everything that we talk about in the course, this is also the resource for you. This is a hands-on workshop because we are providing remote access to a number of people who can connect to a training server and follow along with the exercises that I do in the second half of the broadcast. If you don't have remote access, you can still follow along in the second hour. Also, one of the features of this course, if you attend 6 sessions or more, we will be happy to issue to you a certificate of accomplishment in the fundamental level for the completion of this course. And visit us at colfaxresearch.com. A lot of free information on parallel programming, specifically on Intel architecture. We have downloadable code for case studies and tutorials. We have presentations, video courses, all here. As a matter of refreshing earlier material, I want to again point out that we are discussing Intel Xeon processor programming and Intel Xeon Phi coprocessor programming. And we are able to do this in one course because really you can have one application code that is expressed in C, C++, or Fortran, parallelized with automatic vectorization, OpenMP or MPI, and/or MPI, and this single code runs well on both platforms. Hopefully you were able to see this trend from all of the practical exercises that we did. We propose a methodology for performance optimization, and we focus on performance optimization of a given algorithm, meaning we do not discuss how to pick a good algorithm to solve your discretized natural sciences problem. We are talking about expressing this algorithm in code so that it runs on hardware efficiently, handling parallelism and memory traffic optimally. And we propose a roadmap, a methodology for optimization. You need to visit 5 optimization areas: scalar optimization, vectorization, multithreading, memory access, and communication. We had dedicated sessions on the first 4. We did not really discuss distributed computing, so we did not focus on communication, but this is explored in detail in our book. And also the labs that you have access to on your training servers. Some of the labs address offload traffic and MPI communication. So having discussed these optimization areas for your code, I want to now present to you tools that make it easier to see opportunities for optimization, and also tools that allow you to get optimized performance without really tremendous effort. Notice that whenever I show performance results, I will be comparing a Xeon Phi coprocessor to a dual socket Xeon, so that I'm comparing devices of similar thermal design power. I've addressed this many times in this course. So one of the tools that helps you to get performance without much coding is the Intel Math Kernel Library, or MKL for short. MKL comes with Intel Parallel Studio XE. So even in the minimal Composer edition, Parallel Studio contains MKL. And I believe that MKL has recently gone free. Let me search. Yes, there are options for getting the Math Kernel library at no cost in certain specific cases. So you can search for MKL free or no cost MKL, and this is an opportunity. So Intel Math Kernel library comes in the form of binaries, which have implementations of special mathematical functions optimized for Xeon architecture and for the Xeon Phi architecture. This diagram shows the areas which MKL covers. It is a bit misleading because I'm showing these areas of the same size, but really the biggest use of MKL is linear algebra and fast Fourier transforms. Linear algebra in MKL comes in the form of support for BLAS, LAPACK, and scalable LAPACK routines, and also sparse solvers. So these are all linear algebra routines for operating with vectors, with matrices, and for solving systems of linear algebraic equations. Fast Fourier transforms are supported one-dimensional and multi-dimensional, both multi-threaded and cluster FFTs. So, and in addition, something you will probably find useful is random number generators in MKL. MKL has support for random number generators that can be used in a thread-safe mode. So all of these functions have multi-threading built in, they have vectorization built in, and they handle memory efficiently so that you get good performance on Intel architecture. Well, MKL started originally as a library for Intel processors. It is being updated for Intel Xeon Phi coprocessors, and the key functionality is already optimized for Xeon Phi. You will find probably some functions that are not yet optimized for Xeon Phi, but they will at least run on Xeon Phi. In addition to the functionality that I mentioned, linear algebra, fast Fourier transforms, and random number generators, MKL also has support for vector math, which is useful for computing transcendental functions on arrays. There's some statistics analysis tools and data fitting routines. I want to focus on using MKL with Intel Xeon Phi coprocessors because there is no special tricks for using MKL with regular processors, but with Xeon Phi you have three options to use MKL. One option is to use MKL as if you were using it on the CPU, but in the native programming model for Xeon Phi. You remember the native programming model from the very first session in this workshop. If you missed the very first session, you can always revisit it. We discussed the native programming model where your application runs entirely on the Xeon Phi coprocessor, and to cross-compile for it, you have to use the argument -mmic, and then you copy your executable and you run it on the Xeon Phi. To have an application that uses MKL, you also have to use the compiler argument -mkl, and then your application may be able to find the MKL library binaries on Xeon Phi and use them in the native mode. There is another way to use Xeon Phi coprocessors with MKL, and that is automatic offload. In automatic offload, you write your application as if it was written for the CPU, and you compile it with -mkl, and you run it on the host. But prior to running it, you set the environment variable mkl mic enable equals 1. What this variable does is it tells MKL to search at runtime for a Xeon Phi coprocessor. And if there is a Xeon Phi coprocessor, then MKL will automatically offload some of the calculations to Xeon Phi. Now, I used the word some, and this is very important. First of all, not every function in MKL is supported for execution on Xeon Phi in the automatic offload mode, and I will show the list of these functions in the next slide. And another reason I used the word some is that MKL actually checks for the problem size. Usually, the bigger the problem, the more sense it makes to do offload. For a small problem, offload may be too expensive because you spend a lot of time transferring the data, and the benefit that you get from Xeon Phi is not significant. So MKL will check for the problem size, and if the problem size is large enough, according to some heuristic analysis built into MKL, then it will do automatic offload. Otherwise, the code will run on the host. But what do you have to do in the code to make this happen? Nothing. You write the code as if it is designed for the normal Xeon processor, and it will automatically find Xeon Phi or multiple Xeon Phi coprocessors if they are available. The third way to use Xeon Phi with MKL is compiler-assisted offload. In this case, you do have to modify your code. You have to insert directives such as pragma offload target mic, and these are directives that we discussed in session number 2 on September 10th, and you can watch this session if you want to learn more about offload. So you will modify your code by inserting some directives, and you will call MKL functions from the offload region. In this case, you just compile with -mkl, you run the code on the host, and you don't have to set any environment variables to make offload happen. To illustrate potential performance benefits from using Xeon Phi coprocessors, I have this benchmark. The benchmark shows performance, higher is better, of 4 functions in MKL on a Xeon and on a Xeon Phi coprocessor. And wherever I use the word host system or the CPU or the Xeon, I mean a dual socket Intel E5 2697 V2 processor, so a high-end CPU. The first set of bars is the performance of double precision general matrix-matrix multiplication on the host and on the Xeon Phi coprocessor. In double precision, Xeon Phi delivers almost 1 teraflop per second of performance, and Xeon delivers about half of that. Another function, and these are measurements in the native programming model. So there is no data movement between the CPU and the Xeon Phi. Another function that I'm demonstrating here is the LU decomposition function. LU decomposition is a standard method in numerical linear algebra. It is used to set up for solving systems of linear algebraic equations. Again, Xeon Phi with MKL works faster than Xeon by about a factor of 1.5. I'm also benchmarking FFTs. Fast Fourier transforms work best on Xeon Phi if you are doing transforms that are not very large. Here n, the size of the transform is 2048. And in addition, you have to supply a batch of transforms for MKL to do, and then it works particularly well. Finally, I'm benchmarking random number generation. I'm reporting results in gigabytes per second, not gigaflops per second. It was a little difficult to benchmark random number generation because you actually generate it faster than you can write. You generate random numbers on Xeon Phi faster than you can write it to memory, so the benchmark had to be tuned to stay within the cache. Importantly, these random numbers are generated with multiple threads in a thread-safe way, and vectorization is used inside of every core. Having shown the potential performance benefits, I want to show the potential performance benefits in the automatic offload mode. In the automatic offload mode, you will write your application as if it knows nothing about Xeon Phi. And then you will call MKL functions from the body of the code. And if you compile it with -mkl and you set a certain environment variable, then at runtime, automatically offload will happen. So here I'm benchmarking double precision general matrix-matrix multiplication. I'm compiling it just like that. And you can see that I'm doing a little bit of tuning. I'm setting the number of threads for my run. I'm setting affinity of threads, and I'm setting affinity of threads on Xeon Phi. And I'm also setting up MKL mic enable to enable automatic offload. So when I run, the application will automatically detect coprocessors and run there. This is the list of functions that support automatic offload. So question mark stands for either D in double precision or S for single precision. MKL will automatically offload general matrix-matrix multiplication, general matrix-matrix multiplication when one of the matrices is symmetric, multiplication when one of the matrices is triangular. I don't remember what this function is, but this is also a linear algebra method. LU decomposition will be offloaded. This is, I think this is the solution of systems of linear algebraic equations. This is QR decomposition. Oh, this is Cholesky decomposition. This is QR decomposition. And this is the solution of systems of linear algebraic equations. Two questions came in from different people to the same effect. How about complex? How about the complex implementation? And to be honest, I don't remember what about the complex implementation, so we will find it out right now. So I will search for Intel MKL, and I think I already know how to navigate. So I need to go to product support, documentation, and I want the HTML, the library reference in C. And here I think I can find automatic offload. Um, well, let's see here. How about so solution of systems of linear algebraic equations. This is one. This is definitely supported for automatic offload. So it supports C for single precision complex and Z for double precision complex, and let's see if it's supported for automatic offload. Maybe they don't specify this. According to not having any disclaimers, I would say that probably automatic offload is supported for complex data. I see no reason why it wouldn't be. So we will probably test it in the we will try to test it in the hands-on part. I wanted to show these performance numbers. They are interesting. This is the performance of DGEM. This is weak scaling, meaning I change the problem size as I use different devices. But these first two are just native execution on the host and native on Xeon Phi. And that is symmetric heterogeneous execution. I'm using Xeon together with Xeon Phi in the automatic offload model. It doesn't make sense to use it for this small problem that I had, but automatic offload model can actually handle problems that are large enough to fit in the host memory. Even if this problem is too big for Xeon Phi, automatic offload will partition up my matrix and offload parts of it to Xeon Phi. And I mentioned that this is symmetric heterogeneous execution, meaning I use the Xeon and the Xeon Phi simultaneously. How did I do this in code? I actually didn't do anything at all. In the code, I just called matrix multiplication. Then I set up these environment variables, and MKL automatically detected how to team up the host and Xeon Phi. So the performance that I get is less than Xeon Phi plus Xeon performance, but you have to remember that here I have to transfer data back and forth. But for not doing anything, this is a pretty welcome acceleration. This is even more interesting. This last bar is symmetric heterogeneous execution on a system with a Xeon and 4 Xeon Phi coprocessors. Again, in the automatic offload model, I achieved something like 80% efficiency. So if I compare this number to 4 times this number plus that, I get something like 80% efficiency. But again, what did I have to do in code to scale it across 4 Xeon Phi coprocessors and a Xeon? The answer is nothing. MKL did this for me. So this is a powerful feature, and this is not only for C++ and Fortran code. Actually, if you are a user of R or MATLAB, there are white papers on the Intel side describing how to make use of Xeon Phi in MATLAB or R. If your problem is one of these problems, or it relies on one of these numerical methods, then you can tell R or MATLAB to use MKL as the backend for BLAS or FFT. And then before running your R or MATLAB application, you set the offload variable, automatic offload variable, and possibly you do a little bit of tuning, and then automatically you will start using the performance of Xeon Phi coprocessors in your application. And R or MATLAB do not have to be made explicitly aware of Xeon Phi, they just have to rely on MKL, which will find the Xeon Phi for you and scale across the coprocessors automatically. Well, not all functions are supported for automatic offload, so there is a third way to use Xeon Phi, and this is compiler-assisted offload mode. In this case, you are on your own regarding the setup of offload. You have to specify, you have to insert directives in the code requesting offload. You have to specify how you want to transfer data in and out of the coprocessor. But when you run it, you still run it on the host, compiling with the argument -mkl. So this is a comparison between automatic offload and compiler-assisted offload. In automatic offload, you do not modify any code. In compiler-assisted offload, you actually have to make the code explicitly aware of Xeon Phi. As for specifying what data goes where, you have no control over it in automatic offload, but in the compiler-assisted mode, you have to do that by hand. If you want to use multiple coprocessors, automatic offload will do it for you. Compiler-assisted offload, you have to implement this, and this is not a trivial task. But functions that are supported in the compiler-assisted offload are all of the MKL functions. For automatic offload, only some of the functions are supported. And finally, I wanted to demonstrate the native execution mode. Here I'm generating random numbers. In the left-hand side, I'm generating random numbers with one thread using the C standard library. So I'm calling the rand method, and I'm generating 500 million random numbers. This panel uses MKL to generate random numbers, still in one thread. But look at what I do. I don't have a loop. I used to have a loop when I called the rand method. Now I don't have a loop. Instead of a loop, I initialize the random number generator, and then I call a single function, VSRNG_uniform, meaning run the random number generator, and to this function I feed the array and the size of the array. And it will generate 500 million random numbers for me, but this interface helps MKL to handle vectorization, because if it has to produce multiple random numbers, it can stick calculations into the 16 vector lanes on Xeon Phi and speed up your calculation. The performance difference is huge. So here I'm running it on Xeon Phi with one thread. It takes 50 seconds with the C standard library. With MKL, it takes an order of magnitude less. It is not 7x faster. This is actually more like 11x faster. This is an outdated number, but the performance measurements are fresh. So this is MKL. We will experiment with it in the hands-on part, and we will also experiment with another tool called Intel VTune Amplifier XE. VTune is a performance analysis tool, and I will show a few screenshots just to give you an idea, but I don't want to spend too much time on it because we will actually see it live. So why show screenshots of a tool when I can just demo it? In VTune, you can set it up to run your application, and then it runs the application and collects performance metrics. It does it by relying on performance monitoring units in hardware. So Xeon and Xeon Phi have PMUs. PMU stands for Performance Monitoring Unit, and this unit sits, each core has one, and this unit sits in the core and counts certain metrics, such as how many cycles were counted, how many instructions were retired, because some cycles you cannot retire an instruction. Maybe you're waiting for an instruction from the front end, or maybe you're waiting for the completion of the previous instruction in the backend. It also counts cache misses, branch mispredictions, data page walks, and lots of other metrics that tell you what is happening with your application. Importantly, because this is a separate unit from the core, collecting performance results does not slow down the application. Well, in practice, there will be a minor slowdown because, well, you don't just collect results, you have to record them somehow, and this will use resources. But essentially, your program runs in real time, and you see real-time hardware events. It is useful when you compile the code for VTune to use the argument -g. It embeds symbols in the code so that VTune can show you the hotspots and the resource hogs of your application. Importantly, -g resets your optimization level to 0, so usually you would use -g in combination with 002 or 03. You can use VTune with Xeon-Phi, both for offload and for native applications. And in both cases, you can use a wrapper script to set up environment in your application. And I will show you how to set up VTune in the launch on host or launch on target method for both offload and native applications. Now, things that VTune can show you are, first of all, the summary analysis. The summary analysis will show you performance metrics that are computed from your performance events. And metrics such as CPI rate can tell you a lot. CPI rate is the cycles per instructions rate. So ideally on the Xeon you would like to have 2 instructions per cycle, so the target CPI rate is 0.5. If VTune finds that this metric or any other metric is suspiciously out of the ideal range, it will actually highlight it for you. So this pink highlighting was done automatically, and VTune explains what it means. Also in the summary mode, you can, in the summary tab, you can view the concurrency histogram. This is a histogram showing how much time was spent running different numbers of threads. So ideally, you want your application to be parallel all the time. So you want power to be concentrated here in the ideal range. But if your application has poor load balance, this is what you will see. And this indicates to you that you need to focus on optimization of multi-threading. In contrast, this is optimized application which runs in the fully parallel mode most of the time. VTune can also show you timelines of individual threads, which can help you understand what's happening. For example, these bands are timelines of different OpenMP threads on the host, and gray is what, brown is what you want to see. It means that this is useful work. Orange, you don't want to see. This is spinning and idling. What I like a lot about VTune is that it can show you hotspots of your application. You can see there is a list of functions in this panel, and hotspots are your functions, and VTune shows how much time is spent inside of every function. But even more, you can double-click on the function, and then you will see the code of your application. And VTune will drill down the hotspots down to a single line of code. This is statistical analysis, of course. So when VTune identifies one line of code as having so much time spent there, or so many cache miss events in this line, this is a statistical result. So sometimes VTune may be off by one line, and the documentation actually describes how accurate you can expect VTune to be. But if you have enough statistical data, you can expect this analysis to be fairly accurate. Something else, an indirect benefit of VTune that I like, is you can click on any line and VTune will show in the right-hand side panel the assembly corresponding to this line. This is very powerful because if you need to study assembly for a certain application, you could potentially use the compiler to produce the assembly listing. In the cases of vectorized loops, this may not be very helpful, because with vectorized loops, the compiler often prepares to handle misalignment with peel loops, and it often prepares to handle situations where the number of threads is not a multiple of the vector length using remainder loops. And the compiler is also able to fall back to scalar calculation instead of vectorized calculation if you have vector dependence at runtime. So the compiler will implement all these code paths, and if you study the assembly listing produced by the compiler, it will be very difficult to find what exactly is going to happen at runtime. But in VTune, you actually have measurements of what's happening at runtime, so you can immediately find the branch which is actually taken at runtime. I will not show more about VTune in slides because I want to save time and show it live. So I've demonstrated just two software development tools: Intel Math Kernel Library and Intel VTune Amplifier XE. Intel Parallel Studio contains a lot of other software development tools that not necessarily focus on performance. There are tools that can help you with analyzing vectorization usage, and tools that can help you decide how to implement parallelism in your application, tools that can detect memory issues. But there's no time to focus on it in this training. I want to go on to the hands-on part a little bit early today. And before I conclude with the slides, I wanted to leave a few references. So these slides are available online at this page. Once you get the slides, you can take advantage of the clickable links in this PDF document. So this workshop is recorded. Slides and recordings are posted here. If you want to sign up for one of the future workshops, this is the page. Intel has run a number of webinars on specifically on software development tools, and they are available here. Visit the Intel Code Modernization Program. This is a hub for training resources and case studies focusing on code modernization, essentially what we've been talking about all along. I'm not saying goodbye just at this point, just preparing to move on to the hands-on part, but want to remind you that if you have remote access, you have remote access for the rest of the day today and for 5 more business days starting tomorrow. You can use it for anything you want. You can run your own applications, or you can stay tuned to your email. I will send out suggestions for exercises that you can do with your training server. Let's begin our customary 2-minute break, during which I will set up remote connection to my training server. See you in 2 minutes. All right, I think we can start. And today, in our labs, I am going to chapter 5, which has exercises for MKL and VTune. So let's begin in the chapter about MKL. And as usual, I will open the code. And I will compile it. The code benchmarks the function dgem. This is the double precision general matrix multiplication. And I want to, first of all, be able to run it on the host. And also, I will try to use it on the Xeon Phi coprocessor. So on the host, the makefile suggests that I set up the number of threads and the affinity before I run it. But let me try not doing this and see what happens if I run it on my CPU. So it uses as many threads as I have logical processors, and there is no affinity set. In fact, I have to tell you that MKL is designed so that if you have hyperthreading enabled, it will actually use half of the threads. So even though OpenMP, which is the backend for MKL, is set up to use 24 threads by default, MKL will fall back to 12. The performance that I'm getting in double precision on my CPU is 120 gigaflops per second. And I claim that I can get better performance if I set up affinity. And to understand what's happening with my affinity, I want to run a tool in a separate window, and the tool will be mpstat, and I always have to remember how to run it. So I need to do all threads, I think this is right. I just need to expand this. No. Yes, this is better. So I ran mpstat-p, then all in capitals, and then the number 1. This means that I want to show information about my processors with updates every second. No? Oh, I'm sorry. This is what I ran. Okay, so I have 24 logical processors. They are shown here. And let's see what happens when I run my application on the host. You can see that half of them are empty. So yes, MKL is using only as many threads as I have physical cores. Well, that's how it likes it. So let's try to experiment with affinity. First, I will try EMP affinity scatter. And this should place threads far apart from each other. I can't see that I see the pattern that I was hoping to see. How about, in addition, we'll do this. Yes, now it makes sense. So the pattern that I see is that these first 12 logical processors are occupied, and those other 12 logical processors are not occupied. And in fact, if I run CPU info, I will see that the first 12 logical processors correspond to thread number 0 on different cores on package 0 and package 1. So this is what I want. MKL used different cores, 1 thread per core. I could try a different approach if I said affinity to compact, then MKL would utilize, see, these 6 and those 6, but they are actually on the same CPU. So when I set affinity compact and I have hyperthreading enabled, I'm only populating one CPU. I could do compact, comma, 1, and this would permute the order in which logical processors are enumerated, so I'm back to using the threads that I want. So I think compact gives me about the same compact, comma 1 gives me the same performance as scatter on the host. Okay, so I'm happy with the host performance. Let's see what I can do on Xeon Phi. Well, how am I going to run this on Xeon Phi? I compiled an application in the native programming model, and I can try to copy it to Xeon Phi. I will go along with it. I will try to run it. It cannot run because I have not set up the library path for it. So I will set the library path as I know it, opt-intel mkl lib mic. This is to find the mic implementation of mkl. And this is only possible because I am NFS mounting opt-intel from the host onto Xeon Phi. And also to find other Intel libraries, opt-intel libmic. That's what I did. So now I'm running. And to see what's happening on Xeon Phi, I will run another command. I will run, instead of this, I will run mic control, mic smc-c. So this lists core utilization of microprocessors. And I will actually just do it for mic 0. And I will loop this. Watch every 5 seconds this. So I can see that my Xeon Phi is now being utilized, and I'm getting 320 gigaflops per second. But I can do better. We saw that with affinity settings, I can do better. So on Xeon Phi, I will try to set affinity KMP affinity scatter. This actually will not change the results because scatter happens to be the default affinity on Xeon Phi. But if I set it to compact on Xeon 5, this really works for MKL. So performance has doubled. Alright, so now I know how to get good performance on the host. I know how to get good performance on Xeon Phi. How about I try using them all together? So let me run this performance monitor for the host once again. And I will now go back to my application. I will type exit, and this brings me back to the host. So I have my application app CPU compiled for the host. This application knows nothing about Xeon Phi. How do I make use of it automatically? My claim is that all I have to do is set export mic mkl enable equals 1. And then when I run, some magic will happen. And I'm running on the host the CPU application. You can see a little delay. So what's happening now? I am using my host CPU, and I'm not using the Xeon Phi. This is not what I wanted, and the problem is that I typed this wrong. It should be mkl mic enable. So now I hope it's going to work. Yes, so now this is the correct syntax. I am using my host, and you can see that I also have utilization on Xeon Phi. The performance is much better than I got on the host, but still less than I got on Xeon Phi. I would like to see more than on Xeon Phi because I have two devices working for me. So how about I try to do a little bit of tuning? So I know that on the host, I had to set KMP affinity equals compact with granularity 1 because with permute set to 1 because I have hyperthreading enabled, and also granularity equals fine. So when I do that, what's going to happen? I have load on the host, I have load on Xeon Phi. The performance is still not stellar. That is because I did nothing to tune the performance on Xeon Phi. And to tune the performance on Xeon Phi, I think I have to do this. MKL has this variable reserved, mic KMP affinity, and we'll set it to compact. And now let's see what happens. Now this is better, and this is better than 1 Xeon Phi. But I want to show you a little surprise here. My system actually has two Xeon Phi coprocessors. I will now run a graphical performance monitoring tool and execute my application again. And what I see is that now I have utilization on both Xeon Phi coprocessors. So I'm actually using two Xeon Phi coprocessors and the host. Well, the result is not uh, much faster than on the host, but it is pretty good. And I had to do some tuning, so let's recall what I did. I had to set MKL mic enable to just enable automatic offload. Then I had to set this variable to tune affinity on the host, and then I had to set this variable to set affinity on Xeon Phi. And that's all I had to do. My code knows nothing about Xeon Phi, it just scales automatically by MKL. We are not getting performance that is hugely different from native performance on Xeon Phi, but if most of my application runs on the host and I have to do offload anyway, well, I will have to move my data back and forth. At this point, I think the problem is just not large enough to compensate for the overhead of offload. If our problem was larger, and we can simulate this by giving it a different problem size, then potentially we could see greater performance. So I increased the problem size by a factor of 5. So the runtime should increase by a factor of 125. But let's I'm inclined to just let it run and then see the performance results. I can marvel at both of my Xeon Phi coprocessors being utilized. If I was sitting in the same room as this workstation, I would have I would hear it. I would hear the fans roaring. You can see that the memory usage does not hit the peak on Xeon Phi, even though this matrix, 40,000 by 40,000, is huge. It is 40 gigabytes in size, and actually the three of the matrices are 40 gigabytes in size. So on Xeon Phi, MKL only allocates as much memory as it needs for the immediate calculation. But on the host, if I go and run the system monitor, on the host you saw that I allocated around 40 gigabytes of RAM. And obviously I have threads running on the host. So this was the first iteration. It's usually slower than the other iterations. And let's wait for the second iteration. This will give us a better idea of sustained performance with two Xeon Phi coprocessors and Xeon Phi and a Xeon. While we're waiting, I can demo this interface. So by default, the view shows the utilization, processor temperature, memory usage, and power usage for each Xeon Phi. I can click here, and this will show other metrics. It will show a plot of these metrics. And I can also click here to see the core utilization histogram. Well, looks like this is the sustained performance. So with two Xeon Phi processors and one Xeon, I get 1.5 teraflop per second. Doing the math in my head, I think this is about 70% efficient. So let's not spend any more time on this. So this was an illustration of MKL, and as I promised, we will try to see if complex numbers are supported for automatic offload. And for this, I will have to go to my code and modify it. So this will also be a good opportunity to see how MKL works. So my matrices will have to change the type. And now the type is double, but MKL actually has a special type for complex numbers. And I will be able to find it here. Laypack complex double. So let's search for dgem, and then we will see all the C plus gem. So if you want to run it in double precision with complex numbers, then this is the interface. The type of numbers is going to be I'm looking for the name of the type. Some reason it's not here. So I probably need to go to interface conventions. Is it? Yes, there we go, data types. This is wrong. Well, it looks like the interface of gem expects the type void, so it will take any pointer. So I will save our time. I don't remember what the name of the type is, so I will keep it as double, and I will just increase the amount of memory that I have there. So what else do I have to do? I will double this. This is not really going to set complex numbers as I wanted, but we can find the type for these numbers later. And here, instead of dgem, I will call zgem. Now let's see if it compiles. So there is a scaling factor, which now has to be a complex number. So let's do that. I will give it a reference to S1, and here I will give it a reference to S2. I don't care about initializing them because we only want to look at performance. So I will set KMP affinity compact granularity fine. Oh, I have to set compact comma 1 granularity fine. This is because I have actually I don't have to set it because it's already set earlier, just a few minutes ago. Yeah, this is not good because something was not initialized. Let's see. Still not initialized. Did I miss something in the syntax? So layout, row major, no transposition, no transposition. M, N, K, then alpha. Oh, thank you. Somebody just commented on the scaling factor, and somebody else has just found the correct data type. So let's try to use the correct data types and see if that helps. So I have to include mkl types.h, and inside of mkl types.h I can find what I need. So the file is opt-intel include mkl mkl include mkl types.h, and if I search for complex, there it is, mkl complex 8, mkl complex 16. So let's make the matrices mkl complex 16, and this will have to be done for A, B, and C. So is that correct? Thank you. We have very courteous users correcting my bugs as I go. So this also has to be MKL complex. And there I will have to pass this. So is that enough? So double I is not going to cut it now. A of I is going to be double I. How do we do it? I'll just set everything like this. This compiles, and I have to run the executable separately. Okay, now it's computing, so the types were throwing it off. It is so it's actually because I have all my environment variables set. It's actually computing on the host together with the Xeon Phi coprocessors. So we have our answer immediately. Yes, the answer is yes, because I see utilization on the host and on Xeon Phi. Automatic offload is supported for complex numbers. And just to show what was happening, maybe also increase the problem size to have a more meaningful scalability. Yeah, we are now doing automatic offload of complex numbers. It should take much less than a minute. Okay, so this is the sustained performance, and if I wanted to disable automatic offload, I will type unset mkl mic enable, export it, and then when I run, the application will run on the host CPU. Nothing is running on Xeon Phi, and well, we will know performance soon enough. So there it is. Well, this is MKL. MKL obviously has a lot more to learn about. For instance, one of the functionality that I wanted to show is the MKL link line advisor. MKL has a layered approach to its architecture, meaning that you will only link the layers of the library that you need. Usually, when you compile for MKL, the link flag is -mkl, just like we saw in this code. We compile with -mkl. But there are situations where you might want to use different flags, and this is when you are compiling for when you, for example, are compiling with a non-Intel compiler, or if you also want to use distributed calculation with MKL. Let me show you what you can do in this case. So I've searched for a link line advisor, and the link line advisor is this web page with an interactive interface. I can pick whatever MKL version I'm using, operating system, whether I want to use Xeon Phi or not. For example, no Xeon Phi, and I'm compiling with GNU Fortran for the Intel 64 architecture. I want to do dynamic linking 64-bit integer interface, threading with OpenMP, and I want to use the GNU OpenMP library. And then the output, or suppose I want to use also clustered calculations with mpich. It gives me the link line arguments and the compiler options that I have to use with this compiler for for the target architecture. Let's wrap up the discussion of MKL. I hope this was enough information to get started. I would like to switch over to the next lab, which showcases another software development tool, Intel VTune Amplifier XE. If you have any follow-up questions on MKL, feel free to type them in the questions box as I reconfigure my system. I will have to go to labs, to lab 502. This is the code that I'm dealing with. And just to make it a little bit more fun, I will modify this code slightly. So this is the code that we saw in session 8, where we talked about load balancing. What this lab does is it creates 20,000 systems of linear algebraic equations, and then it distributes these systems of linear algebraic equations across different threads, and in each thread it calls an iterative Jacobi solver for the system of linear algebraic equations. And this is what we are timing. We are timing the parallel loop that processes all the 20,000 systems of equations. So to make it a little bit more fun, I will do this. I will call another function, which is a wrapper, and I will pass to it all of these parameters. So this function, I will put, if you, you don't have to follow this with me. If you don't do these code modifications, you will still be able to see VTune at work on your system. So n, m, b, x, and accuracy is going to be an array. So I inserted this intermediate function so that I can showcase one of the functionalities in VTune, which is the top-bottom view. So it doesn't compile because this has to be accuracy. And I probably misspelled this. And m is undefined because I have to make it capitalized. And one more modification that I will do is here I will insert schedule runtime. So let me run this application on the host. And this is what happens. It distributes 20,000 systems of linear algebraic equations across all of my threads. It solves them, and this is the time that it takes to solve the system of linear algebraic equations. So if I wanted to see where my performance optimization opportunities are, I would try to run it in VTune. So for convenience, I've created a few scripts here, such as this one, run on CPU. What's inside of the script? Well, it sets environment variables, which may or may not be useful. It also sets some other environment variables that could affect the performance of my application, but let's see what happens when I run it. Actually, let me get rid of this one, because this is what we will do after running VTune. So if I run the script run on CPU, I get just the same results. So now it is time to start VTune. And VTune has a graphical user interface. I am going to demonstrate it in my remote desktop window. If you are connecting through a terminal, I do not recommend running VTune. Even if you do X agent forwarding, it will be very slow and it will eat a lot of bandwidth. So either follow along with me and then connect through the remote desktop, or use your remote desktop now. So to start VTune, I will start Amplifier GUI. Actually, before I do this, let me run something to clean up anything that I had earlier from earlier labs. So VTune stores all, yes, VTune stores all projects in Intel Ample XE projects in your user home directory. I have some garbage there from earlier events, so I will remove this and start fresh. Ample XE GUI starts the graphical user interface version of VTune. This is the window, and it is inviting me to create a new project. So a project will involve an executable and some performance results. I can have multiple performance results for a project. And let me call this project Jacobi Solver on CPU. Then it suggests to me to choose the target system. I will choose the local system. Target type, launch application, this is what I want. The application, for the application, I really like to choose not the executable, but a wrapper script. It is useful on the host, but it is very useful on Xeon Phi, as we will see. I don't need any parameters. This is the working directory. That's all good. I could potentially set up environment variables here, but on Xeon Phi that wouldn't work. So I want to check, yes, everything is good. Now I have this project. It shows in this panel. And if I want to run, I have to run analysis, I can click this button, New Analysis. VTune detects what happens, what my system is like, and it shows the different types of analysis that I can run. So basic hotspots is just the timer. It actually doesn't need performance monitoring units. Advanced hotspots will require performance monitoring units because it will also collect how many instructions were retired, and there's general exploration that collects a lot more events. So I will probably choose this one, and let me click collect stacks so that I can see dependencies between the different functions. I have a Sandy Bridge processor, so I could potentially do these types of analysis. I'm ready to click Start to begin the analysis, but I want to point out that there is this button, Command Line. It allows you to copy-paste a line that you can run in a text terminal. For example, if you are profiling an application on a cluster, you can use this line to collect analysis on the cluster, collect performance metrics on the cluster, and then bring back the results and open them on your workstation with a graphical display. But I will not use it. I'm ready to click Start, but before I click Start, let me switch back to the window where I launched VTune. See, this is the terminal from which I launched Amplifier. Go in, let's see what happens there. I click start, and the application should start running in this terminal. Actually, don't see it. Oh, it did run. I switched a little bit too early. So this is where I ran it, and then it produced this output. You can see that the application was slowed down just slightly compared to the initial run. And now VTune is finalizing results. This might take some time depending on your system, because it's actually dealing with a lot of data. We can see that it created in your home directory under Intel Amplifier projects. It created this project, Jacobi Solver on CPU. Inside of this directory, there's this first analysis, run 000, general exploration, and I can actually check. There's 200 of megabytes of data here. So VTune has to populate a database in memory with this much data. Let's give it a minute. So this is the analysis result. As you can see, there's several tabs. I think they're called not tabs, but views in VTune documentation. This is the summary view. It shows me the elapsed time, the CPI rate, and it is highlighted in, yeah, that's what's happening. Sometimes VTune wakes up cranky. It is highlighted in pink, showing that this is a suspiciously high value. And I can mouse over, no, interface. Yeah, I can mouse over any of the metric, and I get inline help explaining what this means and what to focus on. This view also shows a breakdown of the runtime by filled pipeline slots and unfilled pipeline slots. So filled pipeline slots means that an instruction was retired, and I'm just waiting for the math to crunch. So this is what's happening here. It also quotes to me that 30% of my instructions were vector. Now, unfilled pipeline slots actually take most of the time. So this plus that amounts to 1. So filled slots plus back-end bound plus front-end bound amount adds up to 1. So back-end bound slots are those where I'm running a long latency operation, so the core cannot start processing the next instruction. It's waiting for the previous instruction to complete. Some of the instructions are memory bound, and it shows me that I may need to focus on the data reusage in caches. Some of them are core bound, such as long latency arithmetic operations. In my case, this is not the divider. Apparently, this is the non-divider related issues. Front-end bound is a different situation. Front-end bound means that the core could potentially start processing an instruction, but it doesn't have an instruction to process. Basically, it's waiting for the instruction to be loaded from the level 1 instruction cache, or maybe it's waiting for your program to be loaded into the instruction cache. Usually you see a high value here if you have um, very large executable code. Uh, in this case, you can try to improve performance by um, either interprocedural optimization by the compiler or by choosing how you place functions in code and how local you are basically in your code access. I also see the CPU usage histogram. I'm not sure that I believe this metric. Usually I would expect it to be smeared all over the spectrum, but this is a histogram that I discussed earlier. There's a list of all the hardware events collected by this analysis, and sometimes you can use these events, combinations of these events, to diagnose certain performance issues. Now I am ready to go to other viewpoints, but let me actually, yes, let's first visit the bottom-up view, not viewpoint, bottom-up view. So the bottom-up view shows the functions that take the most time. The way that it works is if function A calls function B and function B takes the most time, then in the bottom-up view I would see function B. And actually here they are not sorted by how much time they took. They are sorted by the different events that they generated. For example, if you want to see who causes your back-end bound unfilled pipeline slots, which are memory bound, well, you can sort by this metric, and yeah, all the functions will be sorted by the fraction of memory bound unfilled pipeline slots. Or you can sort them by clock ticks, meaning which function took the most time. I find it useful to study the hotspots in a different viewpoint. So there is a switch for viewpoints here. By default, it's set to general exploration viewpoint. I like to set it to hotspots viewpoint. In this case, the metrics shown in the bottom-up view will be the runtime and the concurrency. So the iterative solver is the top hotspot. This is what takes the most time. This is the concurrency metric. I'm not sure it's measured correctly, but also in this view, the timelines of different threads become more informative. You can see that some threads were working all the time. Other threads had idling periods, so this is what I want to fix. So this is what jumps at me as the low-hanging fruit for optimization. There is another viewpoint that I like, which is the top-down tree. The principle of the top-down tree is this. If you have function A calling function B, and function B takes the most time, then you will see function A, and collapsible under it, you will see function B here. So here, for example, I have solve my system. Solve my system takes 47% of the runtime, and it is calling iterative solver, right? This is what my code is doing. I have solved my system, function A, which calls iterative solver, function B. Most of the time is spent here inside of the iterative solver, and this is reflected in the top bottom view. And also iterative solver is calling some other functions, and we can see that relative norm of difference doesn't take any time. All other functions don't take any time. What takes time is probably in the body of the iterative solver. So now I can focus on this by double-clicking, and VTune is going to load for me the code. So to help you see what's happening, I'm going to resize the panels on my screen slightly. So in the hotspots viewpoint, for each line, I have the concurrency and the fraction of the CPU time that it used. In this case, this is not a particularly useful view because, well, from the timelines, we know that we have poor load balance, and from the bottom-up view, you can also see that one of the top hotspots is KMP fork barrier and launch thread. They are related to thread synchronization in OpenMP. So OpenMP is taking a lot of time in my application. In other words, well, and because this is the barrier function, I know that this is load imbalance. But let me go back here. Sometimes this is useful to find what's happening. And when you highlight a line of code and click assembly here, you will immediately see what was running when this line was executed. For example, here I can see that I was using vector instructions for loading, multiplication, and addition. If I scroll up and down, any lines that are highlighted are related to this code, and you can see that I seem to have a remainder loop here, but no peel loop apparently. So I'm concerned here that we didn't see appropriate results. That is because, well, yeah, we didn't see appropriate results for the concurrency histogram. Most of the time it says nothing was happening. And I think this is because we did not eliminate initialization. So let me show you how to do that. Let me run another analysis. I will click Start. But before we go there, I will go to Project Properties, and I will click here, and I will say Resume collection after 1 second. So 1 second is a reasonable initialization time for my particular application that I'm dealing with. And if I want to, well, let me also remove this just in case. So what will happen once I click this button is that VTune will start running my application, but it will only start collection of results 1 second after the start of the application. So initialization will be dropped from the analysis. Hopefully now I will see more results, but you can also see what happens when you run multiple analysis types. I have one tab for run number 000 and another tab for run number 001. And actually I can compare runs. See, I can click here, and this will bring up the interface for comparing results. So this time it took faster to load because I did not collect stacks, but hopefully I will get the proper concurrency histogram. Oh, and I'm actually viewing this in the hotspots viewpoint. See, originally we saw it in the general exploration viewpoint. And this is where I saw the CPI metric, and yeah, this is the CPI rate and pipeline slots. Let's see what the concurrency histogram looks like. The interface is a little laggy. It's still loading, I think. Well, it's best to give it a little time to think. Okay, up a little bit. Yes, now the concurrency histogram is what I expected it to be. Sometime I was running 8 threads, sometime I was running 4 threads, but ideally I want to run all threads at all times. And if I view this in the hotspots viewpoint, then the information in the summary view will change. I still have the concurrency histogram, but now I also have this CPU time, effective time, spin time. And this is where OpenMP can give me some hints. A significant portion of CPU time is spent waiting, it says. And this is how much of the CPU time was spent doing spinning. So I have a lot of hints that my application has poor load balance, and I will fix it just like we did it in session 7. I will fix it by adjusting the scheduling mode. To adjust the scheduling mode, this time I will actually go and edit the wrapper script, and I will set OMP schedule equals guided. And once I did that, let me rerun my calculation. I press play again. So now I'm ready to produce the third analysis result. I start calculation, and it's running in the same window, but you can see that the runtime is much shorter. So VTune is going to show me what changed. So this time I think I will see less spinning, but because I fixed the biggest problem, now other problems will creep up on top of the list. So yes, no spin time, but still a very high CPI rate, very high cycles per instructions rate. But at least I can see in the concurrency histogram that most of the time I was running with ideal concurrency, all threads were working. And now to see what exactly I need to do, well, maybe I can go back to the general exploration viewpoint. And look for hints. And I believe that the next aspect would be memory traffic in this application, because it is really not handled well. I may need to do some loop tiling. But so it says that unfilled pipeline slots were taking 80% of my time, and they are memory bound, 50% of them level 1 cache bound. So I may want to try and improve data reusage in the level 1 cache if I can. So this is the principle of using VTune, and I want to show one more functionality before we switch to running VTune on Xeon Phi. I was running the general exploration analysis all along. This is a very heavyweight analysis. It collects a lot of information. If I wanted to run something lighter, I could just choose advanced hotspots. And advanced hotspots collects just cycles and instructions, and it would just show me where my application is spending the most time. It will be faster to work with this data, less information. But in addition to these analysis types, I can create my own analysis type. I can right-click, and then I can say copy from current, and it will create a custom, allow me to create a custom analysis type. I can create any events that I like. So I can add an event, and you can read about the events in VTune manual, but they are not for the faint-hearted. And this will create a new analysis type. Well, for example, let's analyze the activity of divide operations executed, and then I click OK, and then a new analysis type appears here, and I can run it. So to see exactly what you could do with it, there are resources which I mentioned in my slides. So this is a link to development tool webinars. I hope that there, if you're interested, you can find information about the advanced metrics and how you can interpret them. Especially for the Xeon Phi, this used to be important. At the same time, I know that for Xeon Phi, in the past, we used to have to rely on custom analysis and somewhat and using a calculator basically to get the events that I need. But in the most recent implementation, analysis on Xeon Phi is pretty powerful, and I find that the default analysis types are usually sufficient. So as I mentioned Xeon Phi, let me show how to run something on a Xeon Phi coprocessor in VTune. So let me switch back to my terminal, and I have an application that can run on Xeon Phi in the native mode and in the offload mode. So in the native mode, I have a wrapper script that I can run on the host, and what will happen is I can copy, this wrapper script will actually run on Xeon Phi. I will copy this script to Xeon Phi. I will also copy the executable to Xeon Phi, and then I will log into Xeon Phi and see, can I do this? Can I do run on mic.sh? Yes, apparently it sets all the environment variables and it runs my application. So I can close this project in VTune and create a new project. This is the button to create a new project, and I will call it Jacobi Solver Native on Xeon Phi. And here the target system will be Xeon Phi coprocessor native, and the application I will have to specify the path, and it's called run on mic.sh. This is my wrapper script. I can click OK. It just warns that I will have to close the current project. Yeah, okay, close it. So now a new project appears here. All the old results are still saved, but a new project appeared and I can run analysis. But this time I will have to choose one of the analysis types supported for my architecture, which is Xeon Phi. I can choose advanced hotspots or general exploration. Let's try that. You can see I have a different set of controls. And when I run my application, hopefully no, it didn't run. And that's because I specified the wrong executable name. So I can delete this result if I want and edit my project. This is the button to edit the project. And instead of underscores, apparently I have to use dashes. This is the correct name. Now run analysis and start. Switching back to the terminal, and I see that it's running, and it is running on Xeon Phi. And the principle from here on is the same. I will have the summary view, and then I will have the top, bottom, and the bottom-up views. And this will allow me to find general performance issues with my application, and also to drill down into the code to find hotspots, in other words, functions or lines that take the most time. So I have all the same controls. They will look slightly different. For example, this is the top-down tree for Xeon Phi. If I want to see a more meaningful timeline, I can, well, yeah, the top-down tree looks still just like, I think it missed some of the functions in my analysis, maybe not enough statistics. I can change to the hotspots viewpoint, and it gives me more meaningful timelines. But I think that with Xeon Phi, there's just not enough statistics in that short run that I did. Yeah, it did not even pick up some of the functions, not enough statistics. So this is running a native application. What about an offload application? The approach is the same. I will create a wrapper script. The wrapper script looks like this. It sets up all the variables that I like, and then I can run the wrapper script. It starts my application. I confirm that it is functional. It's running now on Xeon Phi, and to use it in VTune, I will create a new project. And this time, instead in the target system, instead of local, instead of native, I will choose host launch because we are launching our application on the host, but collection is done on Xeon Phi. For the application, I will navigate to that wrapper script. Close the old project, and from here on the principle is the same. Click play. I choose one of the analysis types for the host. I can start. And now the application is running on Xeon Phi. Collection is done on Xeon Phi. Well, VTune is a performance analysis tool that allows you to find general issues with your application and also find hotspots. And this allows you to find the lowest hanging fruit for performance optimization. I am mentioning this in relation to a question that just came in. In the Intel tools workflow, does it make sense to combine VTune together with Advisor, or are these meant to be used separately? The question mentions Intel Parallel Advisor. So before I wrap up this session, I will demonstrate what other tools there are in Parallel Studio XE. And I need to find my way around this page every time I visit. This is not what I needed. I'm trying to find the product comparison chart. Yes, this is what I was looking for. So the other tools that you have in VTune, in Parallel Studio XE, besides the compiler and MKL, are a new library, Data Analytics Acceleration Library, which is, as they call it, more than MKL for data. There's additional threading libraries. There's Intel Advisor. This is a tool that allows you to specify where you might have opportunities in your application for parallelism, and it can tell you how exactly to implement parallelism there and what you can get out of it. So whether or not it makes sense to use it in VTune, to be honest, my opinion, this is a matter of personal preference. Usually, Advisor you would use at a stage where you don't yet have parallelism in your application. VTune you will probably use after that when you have parallelism and now you want to see how to make it more efficient and what the low-hanging fruit for optimization is. There's also Intel Inspector. This is useful for detecting memory issues in parallel applications. Well, VTune we discussed. The Intel MPI library we unfortunately didn't have time to discuss, but this is the framework and library for distributed applications. ITAC is a performance analysis tool for MPI applications. And this is a Parallel Studio Cluster Edition. There's other editions that contain fewer tools if you don't need them, but MKL is included in all editions. I'm ready now to wrap up the entire session and want to remind you that there is one more week where you can use remote access. Stay tuned for email coming from Colfax Research with suggested exercises. Feel free to use your training server for whatever learning experience that you might need. Thank you very much for your attention, for your participation, and I hope this was a useful event. Please leave feedback after the webinar, and also please try to participate in a survey that we will send out invitations for. The survey will ask you general questions about your learning experience and learning expectations. It will help us to improve future events. Thanks again. Have a great rest of the day, everybody. Goodbye.